Okay, so today you're going to see a whole lot of presentations, 11 presentations across four different acts. We've divided them strategically, which you'll be having a look at. You will see work that was born under constraint because some are in hackathons, some are from research labs. These are not just students pitching ideas. These are builders delivering proof. Now, we're going to begin, and my name is Atadana, Operations Lead at AQC, and I'm honored to be your MC today. Thank you, Farai. Now, the first three teams you're about to meet are not building for Africa's future only. They are building for Africa's present and the world, where people go blind from preventable disease, where infrastructure fails under pressure, where malaria still kills. So you're hearing from these three teams. They saw the problem, they picked up the tools and the belt. The first solution we're going to be looking at is QSight Africa. Our first team is working at the intersection of quantum machine learning, QML, and public health. Diabetic retinopathy is one of the leading causes of preventable blindness on the African continent, and I'm sure most of you are familiar with non-communicable diseases. Diabetes is one of them. The problem is not the disease, the problem is the detection. Too late, too expensive, too inaccessible. QSight Africa is building the first quantum classical hybrid AI for diabetic retinopathy, screening designed for African deployment. In short, they created a practical mobile-first tool that brings advanced quantum-enhanced detection to the places and people who need it most without requiring data centers or high-end infrastructure. They've built it already. This team spans Egypt and the United States, and it's born out of the Pan-African Quantum Challenge 25 computer engineers who decided that quantum machine learning should have eyesight, not just win hackathons. So please welcome Brian Garcia Rodriguez and Jana Ahmed. The stage is yours.
Okay, hello, do you hear me well?
Loud and clear.
Okay. Yes, I'm gonna share the screen.
Screen is not yet visible. Yes, we can see your screen now.
Sorry, just a second. Okay, let's show it. No. Slideshow. Okay, then we are Jana and Brian, and we have worked on QSight. It's a quantum enhanced AI for early diabetic retinopathy detection in underserved communities. Okay, so what is the problem right now? There's 24 million African with diabetic retinopathy, and we expect that it's gonna be doubled by 2045. There's less than 10% screening coverage, and 1,200 people lose vision daily, which is a crisis. Okay, why this is happening? Because there's high screening cost and limited specialists and poor infrastructure and lack of accessible tools. So we think why we don't build something. Okay, so our solution, we have tried many models like QNN and variational quantum classifier, hybrid CNN with quantum classifier and quantum kernels. We made a web app. Then you just gonna upload your retina images, your left eyes and right eyes. Then by minutes, it's gonna send you a report and detailed report about your diagnosis. Okay. Am I able to see, this is our web app. You just gonna sign in and start diagnosis, write your info, your mail, your age, everything about you. Okay, like that.
Awesome. So in this part, we're just uploading the eyes.
Okay.
If you're able to. We also included the Humanity functionality for a database of every patient in the clinic might have. This way, uh, the samples can be distributed to AI inference servers, quantum servers, etc.
Yeah,
for
if you
batch
can be louder,
processing.
Brian.
Can you repeat?
Yeah, just a little bit. Sound up.
Oh, speak louder. Oh, speak louder.
Yep.
Yes.
Thank you.
So this is the eyes were uploaded. Now they're being processed, and we also have the functionality for a database built from every single patient, so that can be every clinic would have access to their own, potentially others. But so after the inference, we see the probability, the confidence score per class, and we also included the report generation uh, process
Yeah.
of that. And
Okay.
this would be able to send to their email or WhatsApp and or WhatsApp. Yes,
Okay.
awesome. So a brief demo, and now there's a bit of realism with the data set, and we have to work with. Obviously, there's tremendously more samples of no diabetic retinopathy. So finding a ideal data set is a bit of a challenge itself. So we just put a bit of a brief visualization. So to see the nature of the distributions is just slightly odd or mild, and you can see some of
Right.
the
You're a
correlations
minute out, so please take note.
and imbalance. So some of the things we're dealing with, and okay, just speed forward. Maybe the
Okay.
demo took longer.
And if
Here's some of the model hierarchy architectures we tried
yeah,
forward,
and there
and here's the performance
and
figures, some of
yeah,
them.
and the results. This is what's sent on WhatsApp, and this is what's sent on email. A brief on the doc in the report sent. And maybe this is the next step that we are gonna do: test quantum version transformer and find another data set and clinical validation. So actually, quantum neural network have proven that it's superior and alternative to purely classical systems. It may be scalable and offerable and impactful one day. And that's it. Okay, thank you.
Yes, thank you everyone.
Give it up for them. And thank you to Jana and Brian. Thank you so much for that recap. So what you just saw over there is a mobile first constraint, which is not a limitation. They pivoted to mobile first, looking at the audience they have, and they're going to scale to. So it's a design philosophy: building for the hardest environment produces the most durable solution. And if you are a founder, a health tech investor, and because you can see some messages in the chat box, or a pilot partner in the medical space, QSide Africa is seeking funding and pilot opportunities. The proof of concept is live. The repo is public, as you can see. The only missing ingredient is you. So get in touch and let's see what we could do together. The next is Q Mode by Dlamini and Anthony. So the second team is tackling a problem that is at the heart of every African economy: critical infrastructure. power grids, transport networks, urban systems, the arteries of a continent under constant pressure, underfunded and optimize the tools that weren't built for the scale or complexity Africa faces. So they turn hard real-world problems into quantum energy map, solve them with quantum classical networks, and I'll leave the details for them to tell us. So the team draws strength from four leading institutions across three African continents. Ahmadu Bello University, Nigeria, AIMS, Rwanda, Ghana Communications Technology University, and KNUST. Four institutions, three countries, more than a team, coordination at scale. Please welcome Dlamini and Anthony Vincent Ackhurst. Okay, Anthony, you're being spotlighted. Yes, please go ahead,
Sorry,
Lithle and Anthony.
I was muted. So I was trying to join from the machine, but I've not been added yet. That is why I'm speaking from
Wait
the
one
phone
second.
currently.
It might be a pen.
Right. Dlamini, can
Yes.
you come in? Or okay, Anthony.
Okay, so I will let Lamine do the demonstration since he's connected now, and then maybe if there are any questions, we'll be able to also answer.
Awesome, awesome. Okay, please go ahead, Dlamini. Dlamini, are you able to speak now? Let's hear if you're having any challenges.
Yep, we can move on to the next presenter if they're not ready and setting up.
Okay. All right then. All right then. Okay, so we move on to the next presenter, and that should be Qualeria. The noises were not able to make it to this particular session. So Qualeria, you come in now. So our third team for this particular sequence, so what you might have realized is that most of these are hackathon solutions. And so this is also one of them, a hackathon solution. And it has chosen one of the hardest targets in global health. Malaria kills, and it kills children. It kills working adults. It costs the African continent hundreds of billions in economic output every year. And despite decades of research, the dominant strains, Plasmodium, continue to evolve faster than our drug discovery pipeline. So Qualeria is applying hybrid quantum classical computing to accelerate malaria drug discovery, specifically targeting the identification of potential ligands for the dominant strain of the parasite. This team is grounded at the African Institute of Mathematical Sciences, AIMS, Ghana, one of the most rigorous research institutions on the continent, and this spans Ghana, Cameroon, and Togo. Augustina has been in the room before. You know her from IYQ, OQI, and AQC Network. Astride as well. Today, they deliver that proof. So welcome, Augustina and Astride.
Thank you very much. Astride, are you there?
Yes, your screen is live. We can see it, Augustina.
Okay. So good day, everyone. My name is Augustina, and I present to you Quantum Leap Against Malaria. So we go to the statistics. Every year, malaria infects over 263 million people and causes about 95% death here in Africa, despite about $4 billion USD spent annually. The problem isn't just about the funding, but it's about the speed. Drug discovery is always slow and often fails to keep up with how fast malaria evolves. So we asked ourselves these questions. What if we could dramatically speed up how we find new drug candidates? And what if we could search smarter and not longer? Because molecules are quantum systems, at Qualeria, we use quantum computing to model molecular interactions in way classical computers can't, and also allowing us to identify promising drug candidates faster and more precisely. So what is our focus? Our focus is on the Plasmodium falciparum. That is the deadliest malaria strain where predicting protein ligand binding is very critical. So using VQE, we built a system that simulates binding energies and help us select the most viable ligands. And instead of us just telling you, we are going to show you the real work that we did. And so without wasting much time, Melvin is going to take us through the demo. Thank you. Melvin, you're muted.
Okay, can you hear me?
Yes.
Can you see my screen, please?
Yes,
Yes.
it's live.
Okay, thank you. For our demo, basically we develop an app, web app, where we have for the homepage relevant information related to how the system works. Basically, we have two main options in our system. First is the upload PDB file, where basically we upload the PDB file and you start the analysis, and you have the dashboard option here. And if you go down, you can have the overview about how the application works and all the steps you're supposed to follow. And now you can even start one analysis. If you please start your analysis here, you start the process. Here is an overview of the main part of our system, where basically you have all the requirements described here. For our first try, we make sure that you need to use a PDB file, and we think we will extend after. And currently, the maximum size of each PDB file is 10 megabit. And the process time is around 5 to 10 minutes. And how it works, basically, you need to upload one PDB file, as I mentioned. I will just select one on my computer. And when you select one, you just select it. And it's possible to select more than one file, but due to the time and all the other constraints, I will just use one file. And when I do it, I can just upload the PDB file here. And when I upload the PDB file, the process will start now. And when the process starts, you have all the main function we're supposed to evaluate during our process. We have the pocket identification, the ligand generation, the ground state energy calculation, the binding energy, and at the end, the final selection one. And for that, we have the dashboard where we can see the previous history about the previous analysis and the current one. And if you click at it, you can see basically we did some other experiment here. We have some of them already finished and some are still running. Here you have the status of each experiment. This one is running and this one is pending. That's why you can have this cross for the status. And now if you have a look of the current running process, you can see basically some of some other part are already finished. Here the pocket identification, you can have a view of the 8 pocket already generated. Here you have all these pocket. You can even you want just highlight the pocket or open it. You can have a zoom on it. You can see and you can select other pocket. You can check all the structure of this pocket. And after that, you can now move to the ligand generation part, where basically you check now for each ligand generated, also the structure. Here, if I select one ligand, I can now show the pocket. The pocket here, I just need to click on it and the pocket will see. And for the ligand, you can just see different color, right? And you can zoom on it and everything. This is some detail about each ligand. I can click on all of different ligand I have here. And then you can move to other stages. I will move
You're a
to...
minute out, please.
Yes, I will move to one which is already finished. This one, basically, when I move here, I can see the ground state energy calculation here. I can open it. And when I open, I can see this one, this is the best ligand, and you have all the property of this ligand. Now, after you can also do the same thing for the binding energy, and you have the summary result of your analysis. Here, you was able to identify 8 different pockets. You did 40 ligand. We compute 24 ground state energy for the 24 select ligand, and you have this the top candidate here. And at the end, you can have the overall detail about the best candidate. Thank you. Augustina, you can continue.
Okay, so to accelerate this, we are seeking funding and also alongside partners who can help us test, validate, and scale this solution. Because at the end of the day, malaria isn't waiting, and neither should innovation wait. And the International Year of Quantum Science reminds us that quantum is not only about theory, but it's about transformation. And at Qualeria, we believe Africa must not stand on the sidelines of the quantum revolution, but then we must protect our people. So this is it. Thank you.
Awesome, awesome. Give it up for them. Malaria isn't waiting, so why should innovation wait? The global pharmaceutical pipeline has an Africa-shaped gap. Malaria is beginning to fill it with quantum methods from the continents most affected. So if you are a pharmaceutical company, a global health funder, or a biotech investor, this is your moment. Qualeria is seeking funding and pilot partnerships right now. This is the urgency. That's the urgency that's staring at us now. Okay, so back to Q mode. Anthony and Lamini, are you able to come up now? You could unmute and just give us a signal as to whether you're able to.
Okay, hi guys, this is Lamini. Can you hear me now?
Right, we can hear you.
Okay, let me try to share my screen. Vincent, you there? Oh, whoa. Okay, sorry guys, I'm having a little bit of network connections. No.
Right, right. So just a quick background before they come in or before they while they are preparing. So this team draws strength from 4 leading institutions across the African continent, and their solution is Q mode and physics-based quantum operating system for infrastructure optimization. So that's basically what we're talking about. Yeah, please go ahead.
Yeah, can you see my screen now? I think I'm sharing it.
Not yet.
Oh, what's happening? Okay, I'm gonna stop sharing and start sharing again.
Right.
Yeah, we could give them time to set up and then allow the next team and then test. We go.
Yeah, please. So what's going on
Okay
here?
then. Okay then.
No worries. Take it easy. No, just things will work. Okay.
Okay, so we move on to the next team, and so this next session is going to be about stacks and tools, and so the first one is SOQ, Signal Orchestrator for Qubits. We saw 4 presentations, 3 presentations earlier on from hackathons building solutions. Now this is an orchestration. So one of the persistent pain points in quantum computing is deceptively simple, knowing what's connected to what. Now, when you're working with quantum hardware, understanding the physical connectivity of your qubits, which qubit is plugged into which port, how the signal pathway flows, is not a trivial problem. It is the difference between reliable computation and costly guesswork. SOQ, the signal orchestrator for qubits, solve this with a clean visual dashboard that maps quantum computer connections so researchers and engineers can stop guessing and start knowing. Robert Bakiaita built this. He's the AQC's national coordinator for Uganda, currently based in Germany, and the founder of AGIS, Afri Quantum Intelligence Solutions. Please welcome Robert Bakiaita.
Thank you very much. Hopefully everyone can hear me.
Yes, we can, but not your image.
I think I got a bit of issue with my camera, but it's gonna be fixed. Yes, my name is Robert. I'm just based in Germany here. I'm going to present signal castrator for qubits. And without any further ado, well, I'll just start sharing my presentation.
Yeah, we can see your face, Robert, in case. Maybe if you just put your background to blur and we get to see your face, that will help.
Okay.
Or yeah, maybe just close the video feed from your camera as well, if that works. Thank you.
Yeah. Can you see?
Yes, Robert, your screen is live. We can, and yeah, you're visible now. Please go ahead.
All right. Okay. Okay. Well, in this case, if you can see my screen, I think you can be able to see my screen.
Yes, we can.
All right. In this case, well, we're having a problem with most of the labs and most of the researchers and scientists having issues with identifying which cable goes where in the quantum relay, basically knowing which equipment connects where, identifying measurement of qubits and so many measurement instruments and so many devices in quantum. As we all know that working with quantum technology, quantum lab and discovery, research and science works with a lot of wires and connections, and we all seen what a quantum computer is basically. Those that have really seen what it is, you deal with the number and lots and lots of cables. So this is what the tool does basically to help and solve that problem that most of the experiments really face. Well, in this case, well, I'm just imagine you have like 50 qubits so to do quantum computing, and you have like, for example, 20 cables to connect in these devices, for example, my microwave generators and cooling systems and so many other measuring devices, and you have like thousands and thousands and thousands of ports. Most of the engineers face these problems and they store those measurements and data on notebooks or Jupyter notebooks or worksheets or text files. So, and they trying to which exactly ruins the experiment basically. And the main problem is backing up and knowing exactly which signal gets to connected to where. So this is where the problem is, and this is what exactly I'm solving. So the tool basically what it does, it chooses a number of qubits and stages the qubits in the terms of different hardware ports, for example, PCB port or RF line cryo or signal generators. It maps all those ports from different qubits. For example, as I said above that, if I'm giving an example of like 50 qubits. So you map all those qubits, trying to relay them to, for example, RF line cryo and signal generator. And then specifically, it visualizes which line is connected, where a signal flows from different devices, and then gets the update graphically, visually, and then later on you save all your settings or your configurations so that another engineer really faces keep track of all those configurations. Those configurations can also be shared by another engineers or updated or kind of like version controlling, basically. The tool has a dashboard, basically, which has a number of where you click add on a qubit, you stage the qubit, you select the port where you're supposed to map and from different qubits, and then you can also map different qubits at a go. You can select one qubit if you really want to work with on a particular qubit, or you can set a number of qubits, for example, a range from 1 to 10, and you drive those 1 to 10 qubits on different lines. And then you can be able to export the configuration to a YAML file or XSV files, and then keep it somewhere for further configurations. Or later on, you can retrieve the configuration and restore your setup configurations to a quantum computer. That's what exactly that tool does. This is step by step. You select a qubit, for example, like 1, 2, 3, and then you stage them in different for the hardware, like I said, flowing from the PCB port for RF line cryo, and then from the signal generator, and then you store the configurations, and then it gives you the output when it is clearly mapped. How it works, you start with a qubit 1, like I said, for example, you end with a qubit 10. If you want to work with a different number of qubits, a range of qubits from 1 to 10, and then you stage those qubits to a different PCB port and another starting port, and then to the ending port in a hardware. And then from there, it gives you the graphical representation of the entire visual results, and then you can be able, without duplications, actually, ranging from 1 to 10. This section, as I said, it saves your configurations in a YAML file. You can export your configuration CSV file or YAML files, which is structured text files. On data, you can be able to upload again the same files, preview the data, confirm the print, and then restore the entire setup. It also has a function of validation and then batching, entire batch, and then give you a snapshot of the configurations. And then gives you the visualization. This is how the visualization may look or will look later. I'm going to give you a demo, how it looks like. And this is how basically it looks. Behind the scene, of course, it checks the existence of the staging or qubit, whether the port exists. If it does, the port exists and you've already done the configurations already, it will not allow you to further go ahead to reconfigure that already existing port and give you the enhancement of constraints of 1 to 1 to stage, which prevents port duplications. And then still restricts the capacity. Brilliant. Yes, sorry about that. And then what matters exactly, no more guessing of work, and then experts share the load exactly, and then you share their work into your teams. Without any further ado, still do a demo quickly. Just let me know if you see my demo, please.
Not yet.
Okay.
We're still seeing the PDF slides.
Oh, okay. Just a second. Share again. Share screen. Share screen. Share screen.
Right, we can see it now.
Yes, brilliant. So this is the signal orchestrator. Like I said, on this side on the left, there is adding single mapping, which if you want to work with a single qubit, and then the middle part where all the drama and all the actual fun starts, where you can do the arranging of the different qubits. For example, you can select the number of qubits 1 to 10, and for example, you can get 10, and then you select a staging point, for example, your PCB port, and then you turn up like, for example, you have an ending stage port. Just a second, I'll start from here. For example, if you want to work with a single qubit, you start with a PCB port, and then select, for example, another PCB port, and then you do the mapping. It will come here, will show you the signal strength from signal flow from for single qubit, how it starts. And then if you want to work with a number of a range of qubits, for example, 1 to 10, so to say, and then you can be able to select a staging point. For example, if I have a staging sample stage for sample holder, and then you want to end with a support 10, and then start from, you can start with number 1, and then end with 10, and then you can do
Right, would appreciate if you could wrap up now, Robert.
Yeah.
Thank you.
So basically, this is how the tool works. In this side, you can be able to help export. It has the export function where you can export the configurations. You can export the configurations, and then the drawing is here. It has a exporting function. You can be able to export the file into a CSV file or YAML file, and then you can be able to generate a file which is already here, and then download the file for further configurations. If you see the file which is already here, which shows the PCB and staging point and starting port basically. So you can as well upload that same file later on for further configurations in case you want to share your configuration with different engineers or do a version control and you don't want to reconfigure existing port if you want to quickly configure different devices. Thank you so much.
Right.
Again, I didn't really conclude basically, but the tool is already there. It's open source. I'll also share the GitHub repo with everything. It's open source. The code is there. It's already built in Python. Everything is already free, and I'm willing to share the code for further control and further development. Thank you so much.
Right. Thank you, Robert. And we'll be having all of these resources gathered somewhere that the community can reconsult them again, even after this event. So yeah, as Robert is saying, it's public, and you can take a look and collaborate and see how you could advance this. Yeah, so he's building from diaspora for the continent, African talent, global reach, sovereign impact. The next we're going to be looking at is BB84 QKD quantum key distribution. And congratulations to the honorees for this year's Turing Award. And they did tremendous work in QKD. And here we are having a presentation in that respect. Post-quantum cryptography is not just a future problem, it's one of the most urgent infrastructure priorities on the planet, as in right now. As quantum computers advance, the classical encryption protocols protecting our financial systems, government communications, and critical digital infrastructure are becoming vulnerable. Harvest now, decrypt later. I'm sure it's a cliche to whoever is here right now. And yeah, these attacks are already a real threat. Africa Quantum Consortium is meeting this heads-on, and most of AQC's hands-on work across the continent this year most especially, focuses on QKD, post-quantum cryptography, PQC, building sovereign quantum security from the ground up under real African constraints. Now, one of the most powerful solutions is quantum key distribution, and now this foundational scheme is BB84. And now, two researchers from Ghana Photonics and Optics Lab at KNUST are going to demonstrate that. Yakubu Bayulu and Mutala Mohammed Ilyasu are MPhil students in one of the most specialized and underfunded areas of quantum science, which is photonics and quantum optics. They are building affordable BB84 setups and using polarization encoded laser pulses. I'm going to leave the details to them. This is Ghana, this is KNUST, this is the Photonics Lab, this is Quantum Communications, being built from Africa's soil. Please welcome Yakubu Bailu and Mutala Mohammed Ilyasu. Right, could you indicate yourselves, Mohammed and Ilyasu? Karim Ibrahim, are you part of this team?
Okay, let's move on, I guess.
Okay, okay. Right, so we would have to proceed to the next, which is TQ simulator, topological quantum simulator from the CQTech in Algeria. Fault-tolerant quantum computing is the holy grail. I hope all of you know what holy grail means. Quantum computers that can correct their own errors in real time, enabling computations of arbitrary depths and complexity. Most approaches to fault-tolerant are years, potentially decades away from practical implementation. Topological quantum computing is one of the most promising pathways, and it remains extraordinarily difficult to simulate. TQSim is an open source Python package designed to simulate topological quantum computing with anions built by CQTech, Constantine Quantum Technologies at the University of Constantine, Algeria. TQSim makes fault-tolerant quantum concepts more accessible for research and education. Please welcome Nasser and Abdul Muhayman.
Thank you. Welcome. Hello, hi all. I will be presenting TQSim. So let's dive straight in. First of all, just a bit of a reminder, what's topological quantum computing? Well, it's a platform which is designed to enable fault-tolerant quantum computation, as was said in the introduction. So its main mechanism is that it will use quasi-particles called anions. So these anions live in two-dimensional space, and you exchange them clockwise and counterclockwise to make quantum computation. So we have here a little diagram from one of our papers, which shows 3 qubits with 4 anions each, and then inside of these blocks, we do the quantum computation. So in the industry, this is the path which Microsoft has chosen. You may have heard of their Majorana chip. But other industry actors, such as Google or Quantinuum, which simulate anions using trapped ions to achieve the same purpose. On our side, we have developed TQSim, which is the only known open source Python package that allows for the simulation of quantum circuits starting from anions. Now, it is already used in education. We have used it for QTitanium with QWord. It's still being used for that purpose. Let's show here a little example of how TQSim operates. So if once you're given a gate here as a braiding sequence, you input it into the TQSim code. So you initialize your quantum circuit, you braid your anions, and then you measure, and then TQSim does all the computation. So this is how a quantum computation looks like with anions. So it's this braid here. And here we can confirm that we indeed do have a NOT gate with the off-diagonal elements here highlighted in green. We can do something a bit more complicated, such as entanglement. So here we have a Bell circuit, which everybody knows, I suppose. We can also do this in TQSim. We need 2 braids, the Hadamard and the C0. The exact same structure applies. We build an anionic circuit, this time with 2 qubits, 3 anions per qubit. We do both braids, and then we measure. We obtain something like this. So for example, here, this is the first qubit, and you can see the Hadamard braid acting on the red anions. And then the C0 does what the C0 does, which is entanglement. So it makes the 2 qubits interact. And the way we will make them interact with anions is that you exchange anions from each of the qubits. Here you can see that the C0 is pretty long. And then at the end, we have this scheme here where we fuse the anions. So we fuse them, and then we measure the fusion outcome, and this is our measurement. Now you can run this simulation in TQSim. And once you run the simulation in TQSim, what you obtain is, well, it's an equal superposition between the 0, 0 and the 1, 1 state, which is exactly what we were looking for. Now, if you want more information on TQSIM, we have a full documentation page. Of course, I will share with you a better version of this notebook, but you can go to the documentation page here, or if you're installing TQSIM, pip install TQSIM, it's very easy. You can use the help utility function from Python on any method or class, and you get a full documentation. Now, what I have shown you here is the latest release version. It's the pre-release version of TQSIM. It only has something called Fibonacci annuals. So these are annuals with specific properties. What we want is more general annual models, and this is exactly what's coming up in TQSIM version 1. It's based on a very foundational theoretical work, which we have been doing at Constantine Quantum Technologies. There will be a paper also coming out, and this will be in version 1. Version 1 will also have more features to allow for better coding. And with this, I thank you all for your attention. Of course, I will share the GitHub link in the chat momentarily.
Right, Nasser. And I can see a comment from Yasmin saying that that's very cool, and they're doing a PhD on topological data analysis. So I believe this is a tool that is coming in right at the time it's needed.
That's superb. That's superb. I will share the GitHub link as said. There will be version 1. Hopefully you'll be able to use it. Someone already used it in a thesis I have learned quite recently. So that's very, very interesting. Yeah, and of course, keyword chat anim.
Right. Thank you very much, Nasser. Thank you so much.
Thank you.
And so if you're a media platform, Quantum Journal, a researcher, PhD student, whoever, you can get in touch and to learn more about this and how to use it and cite them accordingly. Awesome. So we move on to the next team, which is Fluxonium Qubit Research by Ansibet Miruku. So now, this is not an algorithm, not software, not simulation. The physical qubit itself, the fundamental unit of quantum computation, engineered, characterized, and improved. Ansibet is working at the hard frontier of quantum hardware, the slow, precise physics that makes real quantum computers possible. He's advancing fluxonium qubits, one of the most promising superconducting qubit architectures today, and he was at the APS recently to talk more on this work. Leading players include Google Quantum AI, and they're already eyeing fluxonium as a serious route to scalable fault-tolerant quantum hardware. Ansibet spans the United States and Tanzania, building at the global edge while keeping Africa squarely in the frame. This is sovereign quantum capability at the hardware level, and it starts right from Ansibet. Take it up. Ansibet, could you indicate if you're able to talk?
Yeah, I'm able to talk, but my laptop lost the sound this morning. I just have blown your laptop right now to just connect here.
Oh my goodness. Thank you very much for the sacrifice. I don't know if you're sharing a screen now. We cannot see it.
No, not yet. Let me do it. Okay. Just one sec. Did you give me option to share my screen?
I believe you
Did you allow
have
me?
the option to.
Because I don't see the again.
Look,
I get in as a normal audience. Probably I don't have the. I didn't get
okay.
in as a presenter.
Admin, are we able to promote him to the presenter level?
Yeah, let's see. fixing that.
Thank you.
Yeah, that should work. Thank you. Apologies for that.
Right.
Okay. Now I see the.
Yeah,
I
please
see
try
the.
again.
Okay.
Yes,
Can you guys
we can see your screen
my
now.
screen?
Yes.
Okay. Come on. Okay. Can you see my screen?
Yes, it's
Hello?
visible. Please go ahead. Yes.
Okay. Well, this is Answet Miluko. I'm from University of Wisconsin, and I work on Fraxonium qubit. This is basically superconducting qubit where I work on the pushing the edge of coherence time and T1s of Fraxonium. So just to get started, if you can see my screen right here, I don't know if you see this circuit right
we don't
here.
have your screen again. We don't have your screen. I don't know if it's me only.
Give me a second.
Okay, you could be setting up, and then we. Okay, it seems like you're back. I guess let's quickly try that and see if we come back live. And
Do you see my presentation?
We see your presentation now.
Okay, thank you. So here on the left, I show you a circuit for Fraxonium qubit. So this is the typical Hamiltonian for Fraxonium right here. And we do fabricate this device where basically in this Hamiltonian, the way we make it, here you have these arrays of Josephson junctions, which give us this EL in the Hamiltonian. Then you have these capacitance pads, which give us the EC in the Hamiltonian. And then there's this small junction right here, which defines the EJ. So this is how we make these Fraxonium qubits right here. And then after this, actually, so I do the measurements where I do spectroscopy. So below right here, you see this is the Fraxonium spectrum. So it is 0-1 transition right here, this is 0-2, and this is 0-3. So as you can see, the spacing between these transitions is not equal spaced. Now we can basically derive this transition 0-1 and make it our qubit. Again, it's a nice qubit because the harmonicity or the spacing between 0-1 and 0-2 is large, that you can address 0-1 transition independently without affecting the rest of the transitions. So I guess you guys have seen this cryogenic setup, maybe in this kind of picture right here. So now I show you, this is what we, our refrigerator. And then basically this is how we cool down our qubits. And here you have these different flanges, the bottom one, the middle, and there's this right here. So this 4K, this is 100 millikelvin, and this is 7 millikelvin. So each flange right here inside this cryogenic, it gives you a different temperature for your that you can achieve. So below right here, this is the lowest temperature, which is about 700 millikelvin. This is where we put our Fraxonium qubit right here. So we cool down our system to that low temperature, where now basically everything starts to be, to superconduct. So I told you that this device basically using, maybe I was too fast, but we use materials basically on silicon substrate, and also we use aluminum, and we make with these junctions, which is basically oxide. And because of these are the normal material, they come with some loss. So my product actually I do in my work is to understand what are the loss channels that affect my Fraxonium qubit. And the way we do this is basically by doing qubit performance, where you characterize the lifetimes. So here I'm showing you a trace for how we measure the echo time or coherence time. So this is one of our qubit that I did measure actually maybe last month. And the coherence time basically tells you how good is your qubit to keep the phase. And you have this is T1 time, which tells you the life time for the qubit to remain excited. So if you repeat this measurement for a given amount of time, you can see at some point in time, there is some fluctuation, which tells you about the loss in the system. Hello?
Yeah, please, please.
Okay.
Please go ahead. Ansabet will figure that one out.
Okay, so yeah, so they basically my work is to analyze these loss channels by basically doing this qubit characterization to see how we can push the boundary of Fraxonium qubit. I think that was it what I had. If there's, I don't know, if there's a specific question or something like that, I can take it and then yeah.
Right. Thank you very much for that concise presentation, Ansabet. And I believe that whatever link that needs to be posted to get to your work or learn more about what you're doing, you're able to share that so we can share it with the community as well. You can do that in the chat box as well. And
oh yeah. I think I'll go ahead and share our group website where you guys can get more information about our project. I think that would be really good.
Awesome. Thank you very much for that answer.
Thanks.
Okay. So here we are talking about the hardware. So we've just traveled the full quantum stack. We talked about applications in the first section, and now we talked about the hardware. Before we go to the next section, I don't know whether Q mode is ready to come in now before we go to the next section. I believe this is still. Oh, Anthony, is this your screen? Ansabet, your screen is still visible. You might want to stop sharing.
Give me 1 sec.
Okay, and I can see. Okay, you are ready now, Anthony. So you will be next. Please, Ansabet, your screen is still visible.
Yes, I can stop sharing right now.
And yes, Q mode, you are next now. And yeah, so just a quick background while you are spotlighted and you start sharing your screen. A fresher for those who don't know who you are. So shortly, QMOD is a physics-based quantum operating system for infrastructure optimization. So this is an optimization solution which works in power grids, transport, financial systems, urban systems. All of these are the arteries of a country, a continent, and optimization is very important. And the team draws strength from leading institutions on the continent, 4 universities, 3 countries, and from Bello University, Nigeria, AIMS, Rwanda, Ghana Communications Technology University, and KNUST. Welcome to Anthony and Dlamini.
Good afternoon, guys.
Yes, good afternoon. You're loud and clear.
Oh, thank you very much. So as we're here, we're QMOD, so we're gonna be presenting about actually an optimization problem. So, but we're trying to build like a modular infrastructure, whereby the modular infrastructure will contain transportation, energy, and agriculture and climate. But for now, we're more focused on what in energy. Why are we more focused in energy? Just because almost like everything we do in the world requires what energy. So energy is the ability for us to do work. Energy is needed to do all these quantum things that we're doing to distribute something. So it's better like to actually optimize energy first for us to order to do other things. So okay, the main problem for us was actually the main problem was is optimization. But the main problem that we tackled first was power grids. So from power grids, we wanted to optimize what the best possible power supply or to supply what a certain demand. So we called our Q mode. So
can you share your
quantum
full screen?
modularity.
May you share your full screen? Thank you.
Screen. Oh, Vincent,
Yeah,
can you please
please
share
share.
the full screen? Thank you. Oh, okay. We can go to. Can you please go to the next slide, Vincent? Okay. He's called, but he'll continue sharing. Guys, can I continue? Just he'll continue sharing. So then, okay. Most of you will ask, okay, why these guys are trying like to optimize electricity or energy, or what's the benefit for it? What's the benefit for companies or what? For instance, if you do like a little bit of research, you'll find that companies lose about like $60 billion US per year. That not, for example, they are not like we are managing the electricity very wise, or but that I could say. Okay, but our project goes like this. So we have a data set. So we take that data set, we pre-process it like using classical machine learning or any other pre-processing there from data science. Then from there, we discretize it. Then from discretizing it, then we turn it like to a Kubo problem. So from the Kubo problem, we turn it to a Hamiltonian. So from a Hamiltonian, we try to solve that problem adiabatically. Okay. Okay, Vincent, can you please share the screen? Vincent, you there?
Okay. All right. So let's. Okay, you can just narrate it. Then we will put things together.
Okay.
I guess we know. Yeah, we know it back. Okay, you can proceed. Sure.
Okay. All right, thanks. Okay. Actually, okay. This slide just shows what the layers of Q mode. So I guess you guys we will actually share these materials and actually the link to the code, because right now we are actually defragmented, like everything is there and there and there and there, but the code is working, everything is working very well. So I was saying that okay, we solve our problem using quantum adiabatic quantum computing. Then from there we compute the lowest energy states. So we find the lowest energy states from there we find the eigenvectors. So from finding the eigenvectors, we actually reinterpret them back to the data sets. Then from there, we feed it back to a classical machine learning so that it can learn from the problem that it had solved. Then from there, you can dispatch the solution to the grid. So that's actually what we're doing. So why are we actually doing this? What are companies going to benefit? So this system is actually intelligent, efficient, so much so that it allows us to actually put some energy storage in the grids. It will tell you, okay, which node to use to store electricity, which node actually to use to produce like renewable energies, something like that. At the same time, it could also like do some scheduling for your system, so that you can know when to do maintenance on the system for the company, not to use some capital or some money. So it's in real fact is actually it's a real-time system. So for more information, I would actually ask Vincent like to share our GitHub repo for QMod. But from there, like we have other modules. But for now, can we just present the QMod? And from there, I think we will also guys will find the solution from there. Actually, it's easy like to run the software. So that's what QMod is doing, in short.
Right. Thank you very much, Dlamini. For that, we can see the back and forth, but still you were able to come through greatly. I hope you're done.
Okay, yes, I think I'm done. But now I would just like to throw something in. For our team, actually, the only thing that we're having now difficulties that our team is a fragmented team, so we actually need a lot of support when it comes to like hardware Like for instance, the hardware, when it comes to computing hardware, I'm a witness for that. My laptop actually died. We also have like problems with networks, but at the same time, I'm sure that we're a super team. We can actually produce like real results. So that's the actual main challenge that we have for now.
Right. So yeah, I would appreciate the links to your work when you have that in order, and I believe that collaborators will get in touch to see how they could support. Thank you very much for making it to the demo day and for letting the world hear about your work. And we proceed to the next section. So for Mutala, if you are in the room, please indicate. We'd love to hear from you. But we are proceeding to the next group, which is focusing on another solution in health. So this is the third segment, and we're going to look at health again on Parkinson's disease. Parkinson's disease affects over 10 million people worldwide. Early detection is one of the highest impact moves in neurological care. Team Q Medicine asked a sharper question. What happens when you run those detection models on actual quantum hardware? They delivered rigorous head-to-head comparison of classical versus quantum machine learning models for early Parkinson's detection using real biomedical data. Ranasat, Sitana, Afifi, and Shita placed second at the Alexandria Quantum Hackathon based at Zivai City of Science and Technology in Egypt. Please welcome Rana, Sitana, and Ruwaina as they present Q Medicine. Please unmute and indicate if you are in the room. Rana, Jana, and Shita.
Yes, we're
Hi.
here, but we're reading.
Right. Yes, you are noted by the admin who will be promoting you to the presenter status, so you are spotlighted for everyone. Just
Okay,
a
I'm on it.
moment.
Who needs sharing, right?
Yes, Rana. Let me.
Rana can present
Rana.
because yeah.
Okay.
Satana is not still presenter till now, so.
Hi, I'm here.
Okay.
Just put the
You're allowed in.
presentation mode. And... Okay, hello everyone. We are Q Medicine team where quantum AI meet health. Here is our full team, and we won the second place in Alexandria Quantum Hackathon for detecting Parkinson's disease. Parkinson's disease doesn't begin when the tremor appear. It begins long before. Silently, deep in brain, dopamine neurons are dying one by one. But by the time the first symptoms show, nearly 60% are already gone. That is tragedy. By the time we see it, the damage is already serious. Early detection changes everything. It gives us the chance to slow the disease, protect what remains, and preserve quality of life. Because by canceling every second lost in a step, we may never get back. Parkinson's disease is not just a medical condition, it's growing a global crisis. In 2019 alone, over 329,000 lives were lost, more than double the number just 2 decades earlier. And yet, doctors are often forced to act too late. By the time symptoms appear, the damage has already been done. But there is a hope. With AI and emerging technologies like quantum machine learning, we can uncover hidden patterns in voice movement, even brain signals, long before the human eyes can see them. Our mission is simple but urgent. Detect Parkinson early before it takes away mobility, independence, and quality life.
So yeah, thank you.
For
Sabrina.
the data set we used, we had 188 patient and 64 healthy person. The age range between 33 and 87 years, and the data size is 756 instance and 754 features. And our task is binary to detect the person either is patient or healthy. First of all, we do the classical part with two different approaches. The first approach, we use neural network. In processing, we load and process our data. Then we calculate the classes weight. Then for the modeling, we build a neural network model. Then we set the callbacks and we train the model. For train the model, we use voting classifier and use feature engineering, polynomial features, and feature selection. Then we load the best model and plot training history. And finally, we evaluate in the test set. The result we got for the first approach with accuracy 95.29%. For the second approach, we use SVM model. For the data processing, we use min-max scalar, then BCA, and then handle the implants. And then we train the SV model on the trained data, then we evaluate it in the test data. The accuracy we got for this model is 92%. For the most interesting part, for quantum part, Rana will go through it.
Thank you, Satana, for the presentation. And yeah, as Satana mentioned, our classical solution achieved more than 95% accuracy. So why quantum machine learning here? Here it's not about accuracy, it's more about high dimensional powers, beta advantage, and deeper insights quantum systems can provide. But all these benefits depend on future fault-tolerant quantum computers. So we are building it now for that future. And our quantum solution has two main components, VQC and QSVM. And let me go through VQC. Here's how VQC works. First, we encode data into quantum states, then ANSYS applies trainable quantum gates. And finally, we measure the output and feed it back to the optimizer to minimize the loss. And here we can see our results. We didn't stick to one experiment. We run many different configurations, like try to change the number of qubits and see what happened, feature map, answers, and repetitions. And our best configuration achieved 75% accuracy. It was 4 qubits, and that feature map and used also real amplitude answers. And yeah, that result was the simulator. But we didn't stop at simulation. After we won second place in Alexandria Quantum Hackathon, we have been awarded access to IBM real hardware. So we dedicated this access to this project, and we run 18 additional runs on IBM Kingston to see how our models will react and will do in the noise of the quantum computers. And we did the same for the hardware as we did in the simulator. We tried a different experiment and run on across those 18 experiments. The best performing one was the 15 qubit, was the 8 qubit one, and the real amplitude answers. And if you compare that with the results came from the simulator, you can see here was estimated was 75, but here it's the best configuration achieved 74.3. So there is a strong simulator to hardware consistency confirmed, and this proves that our models not only run in theory, it also run within the real noise and the coherence of the quantum hardware. And yeah,
You are a minute
right
out.
now.
Thanks. You are a minute out. Please proceed.
Okay.
Just not fine.
Okay. Okay. So my team Rowena will continue with you the other part of the solution, the QSVM right now.
Okay. Our second quantum approach was quantum SVM. Before touching any quantum circuit, we processed with the 3 steps, as we said in the classical one. Our quantum kernel estimation for each pair of data points, I encode them into an n-qubit circuit, either angle encoding or amplitude encoding. We run it on a simulator. We compared angle and amplitude encoding. Amplitude encoding outperformed all across all 3 matrices. The specificity number matters, specifically in medical screening. It means the model correctly identifies healthy subjects, avoiding costly false alarm. Let's be direct about the comparison. Classical wins on accuracy today, and this is expected. We are in the NISQ era, running on simulators and noisy hardware, but quantum kernels are already capturing meaningful structure in this complex biomedical dataset. The gap will close, and Q-medicine is building the foundation now. Together, we move beyond symptoms towards solutions. Our next step is hardware validation for QSVM, ZZ feature map exploration, and extending beyond voice to movement and brain signal data. And thank you.
Brilliant, brilliant. Thank you very, very much, Q Medicine. There were challenges at the backstage on getting them here, but here they are. A brilliant solution. Congratulations to you on that. Okay, so healthcare AI on quantum hardware is a funding frontier, and you can see that most of these solutions that we've seen are on health, and this is just a testament to the challenges that the community is looking at solving. And if you're a research institution, a hospital system, global health funder, recruiter, Team Q Medicine seeks institutional partners and yeah, for collaboration. So get in touch. So would appreciate if Q Medicine you could share links to resources and publicly available resources that the community can look at. We move on to our next presenter. So a quick note, community, please mute yourselves if you are not presenting for the sanity of the program. Thank you. So our next presentation is Fargo Detect. Africa feeds itself and is increasingly feeding the world. Crop disease detection is one of the highest value applications of AI in African agriculture. Favor Alfred took it further. He brought quantum machine learning to the front. Fargo Detect is a quantum machine learning prototype built with Qiskit. It classifies crop leaves as healthy or diseased using engineered features, and he's going to talk more about that. He's a computer engineering student and a HEGATS fellow under the AQC and Innovate Lab collaboration. Here he is today because he built something that works and something worth showing. Welcome on board, Favor Alfred. You're live. Favor Alfred, could you indicate if you can hear me and if you are ready to? Awesome.
Hello.
We can see your screen.
Yeah, good day, everyone. It's an honor to be here, actually. So I built Fargo Detect. It's basically, why did I choose Fargo Detect? Well, it was my first PML project.
That's the same way they do. When I go PTDF scholarship, they choose the best.
Please proceed. Would
best 20
mute
in
the
each
person.
state. That's the way PTDF did for undergraduate. Maybe that's what they applied for. That's the same thing they used for in
Yeah, please proceed. Favor.
Okay, so I decided to choose this project because I realized that it's an issue that many of us are actually aware of, especially somewhere like here in Africa. So first, we need to know that 40% of crops are lost to diseases yearly, diseases that could have been prevented if they were noticed on time. They could actually have been prevented. It affects the economy. It's about viral. So the problem is that the disease spread and there's late detection. And by the time they detect it, there's already a loss in yield. And then there's loss in income for the farmers. And then the price of such commodities or such crops increase in the market. And then there's supply instability, there's hunger rise. And at the end of it all, you feel it in the economy. That's why we built FAD Group Detect. It is a QML model for crop health classification. So basically, all I did was to take images from a data set that contained images of different kinds of leaf. So it detects the disease from the way the leaves look. So it takes a look at it, it encodes it, and then checks for different other features like the color intensity, the color green, the moisture levels, the texture patterns, and spotting. And then I trained my model on it. Currently, the
We lost you for a moment, Favor.
82.2%. So am I audible?
Your audio is coming through, but it
Okay,
breaks.
thank you. Oh, sorry. The latest model we tested, tomato leaves, because I've been trying to run it, train the model on different kinds of. Then I tested, and this was the result, an 82.2% accuracy. And I set the parameters. At first, it wasn't 82.2. I think I started with about 60 to 70. And then with the right params, I was able to get this. And what is the impact? Now we have early detection, we have reduced loss, higher yield, food security, and even a better economy. And it's aligned with SDG 2. Thank you.
Right, right. And it aligns with SDG 2. I believe that's focused on food security or sustainable food chain. Thank you very much, Favor. And one thing that we forgot to mention was that he was also at the simulation conference at KNUST, which is part of workforce development and education. So thank you very much for representing, and thank you very much for this solution. I believe you're able to share the link to whatever online resources points to this so the community can get in touch. And that is what the HEGAT Fellowship produces. And this is how the AQC ecosystem activates. Three key takeaways. The HEGAT Fellowship pipeline works. Students who enter with curiosity leave with proof of work. And I believe the next session is going to be starting. Favor showed up and showed work. That alone puts him ahead of most students in this space who are still waiting for permission. Now, if you're a mentor, technical advisor, a company who needs to give internship employment, I believe Favor is open for that to get going. So those are the signals. And we move on to the next team, Quantum Random Number Generator. And the presenter is Blessed. Blessed Agbola Jesujoba didn't start in the physics lab. She's the front-end engineer who transitioned through the HEGAT fellowship again, moved past the surface and built this solution. She's here to demo a quantum random number generator. Most randomness is a lie. Classical computers rely on deterministic algorithms, pseudo-randomness that can be predicted if you know the starting point. Quantum is different. It taps into the genuine, irreducible randomness of quantum measurement, and I'm going to leave that to her to talk about. Blessed built the circuit, she ran the hardware. Today she shows you the output of true entropy. And she was also at the simulation event, simulation conference at KNUST. So if you were there as well, I believe you might have seen Blessed or spoken. We can catch base in the chat box. Over to you, Blessed. Let's see the solution. Yes,
Hello, can you
we
hear
can see
me?
your screen. Yes, you are
Okay.
loud and clear. Your screen is visible.
Yeah, my name is Jesu Joba Blessed, and I'll be presenting my project on quantum random number generation. So, as people here have read that the secure systems they are not completely secure. Quantum computing is a threat to them, and many of those systems depend on randomness to stay secure. But the problem is that most of them use what we call pseudo-random number generators. They look random, but they are generated by algorithms. That means that if you have enough information about them, predict you can predict them. So this is the problem that my project is trying to solve. How do we generate and how do we get true randomness, right? So instead of relying on computation, we can rely on physics. In quantum systems, particles can exist in multiple states at once, and when you measure them, the outcome is inherently random. So what I built is a quantum random number generator using QC. I started by initializing the circuits with 5 qubits. Then I placed them into superposition using Adama gates, and I measured them to generate random bit strings. So let me show you. So yeah, each qubit is placed into superposition. The qubit was initialized with 5. The circuit was initialized with 5 qubits, and we used the Adama gate present in superposition, then measured the outcome. And after running the circuit, this is the kind of output that was generated. This bit string occurred like about 640 times and so on and so forth. And seeing this, I believe the question that will come to mind is that how can we say that this system is truly random? How do we know that it is truly random? So I carried out some tests on it. So I did a bit balance test to show the PAQC like its qubit. So for the first qubit, we had a fraction of 0.495, the second one 0.4990, the third one 0.5. So all of them are between plus or minus 0.5. So this tells us that there is a balance. And yeah, the next thing I carried out was the Shannon entropy test. So the randomness quality check for the Shannon entropy was 4.998. So out of 5 qubits, we got this. So so why does randomness matter? Randomness is useful in many aspects like cryptography, secure communications, and scientific simulations. And it is imminent that we secure our systems for the future where quantum computing becomes what's the word? We need to future proof. I mean, we need to quantum proof our systems. Yeah. So that's it. Thank you. Thank you for listening to me. I will share the link to my project in the chat.
Awesome, awesome. Thank you for stepping out. Blessed non-traditional pathways into quantum must be built and honored, and you are proof of that. You did not just have a physics degree, you had a fellowship access and the will, most of all, the will to build. And that is what you have demonstrated. And that is way, way more enough. It's a tremendous proof of work. Thank you for stepping up. And we are waiting to celebrate you and to show you on in whatever trajectory that this project takes. So these are the signals, mentors, lecturers, technical builders. We can collaborate or recruit this talent to develop it further. Awesome. Now we've looked at builders in health, in optimization from Ghana to Nigeria, from Egypt to, I believe, Sudan. And now we're going to look at a broader picture, the ecosystem that produces them, that sustains them, and the compounding impact. Our next presentation is going to be from CQ Tech again. They are presented early on, but we're going to have another one from them. Quantum Outreach and Impact by Abdul Muhayman. Constantine
Thank you.
Oops.
Oh, go ahead, please.
Okay, CQ Tech was founded by Dr. Taha within the University of Constantine Physics Department. What it has become is one of the most productive quantum education and research ecosystems on the continent. Dr. Taha is also co-founder of Cuminex, a quantum and AI-driven discoveries company. And Muhayman was part of the judges at the Quantathon where Qualeria presented. So it's like a full closed loop now. People know each other over here. And that's the background to this story. Thank you very much, Abdul Muhayman. Over to you.
Okay. Thank you so much for the very warm introduction, and I'm really happy to be here, and I'm really surprised by like the presentations that were before me. I'm really happy to see the African talent delivering on the promises. So without short, let's not take much longer. I'm going directly to the presentation. Atadana kind of ruined my first slide. Yes, Xikitech was founded by Dr. Taha in University of Constantine. The vision was for him to set up the first Algerian research group dedicated to quantum technologies. After he finished his PhD, he wanted to establish. He had a dream of establishing this group. And he did establish the group. We worked on, started with ultra cold atoms and then towards topological quantum computing. As you have seen with my colleague Nasser earlier, you have seen the fruits of our work on topological quantum computing, and there were many papers also involved, and eventually TQSIM. And now we are also involved in this era on all aspects, from quantum machine learning to optimization to quantum chemistry. We are working on multiple fields, and that was the vision of Dr. Tahar Wabah, and he did do good on it. On the global side, we are excellent by numbers. So we have proofs since the creation of CQ-Tech. We did compete in many hackathons, 11 or 12, I think, and we won 6 times. 5 of them were first place prizes. On the certificate side, we have achieved more than 800 certificates on the local, and I will talk now about the local talks and the local outreach. We have more than 50 talks and 50 events that we intervened in Algeria and internationally. And we have also had international fellowships, so USA, Canada, the Middle East, Germany. We are representing Africa around the world. Since Dr. Taha established the group, we started learning the field of quantum computing, and topological quantum computing, and then NISQ era quantum computing on our own, and it was hard. It was really difficult for us. The field was a little bit, well, now it's in better shape, but back when CQTech started, the field was still very difficult to get into. So the mission that like kind of came out of that situation was that we need to go through the effort to learn everything, and despite it being hard, but we need to make sure that the people who are going to learn after us, they will have a better experience than ours. So we had the idea to start preparing and teaching, making workshops, making educational materials, contributing as much as possible to making quantum computing a more accessible field. Since then, we have developed 4 workshops in-house. They are completely done by CQTech people. We have a workshop on quantum machine learning, actually a very good workshop on quantum machine learning. Everything was developed from our researchers. We have one on quantum random number generation, as it was presented now. We have one on variational quantum algorithms, and we have one on QKD, and we are still looking to get more. And like Nasser said, through making SDK, the TQSIM SDK, we have also developed a workshop with QWorld, that's QTitanium, that introduces people to topological quantum computing in general, using TQSIM as an educational tool. And we did develop those deliver those workshops multiple times around the country. QTitanium was delivered as part of the first cohort of Q class by Abdullah. Unfortunately, he could not make it today to the AQC. And to push that even further, in April of 2024, we wanted to create Q Algeria to give more access to work with QWorld on. We were already working with QWorld, but to further extend our work with QWorld, and also to give access to Algerian students that are interested in this part of outreach and education, and organizing events for quantum, give them a chance to contribute themselves. So we created Q Algeria. We established it in April 2024 within CQTech, and now we have more members. We have had more members joining. We had last year. We had a continental collaboration that was called Q Africa, where all the African Q cousins joined efforts to deliver workshops to African students, and we were part of that. We delivered Q Bronze and Q Prep, and hopefully some more in the future. We also maintain a Discord for Q Algeria that involves around 300 students and researchers that are doing quantum computing in Algeria, or at least are interested in it. 1 year after the establishment of Q Algeria, February 2025, just a few days after the International Year of Quantum ceremony, we organized Q Nexus, one of our biggest events. It was 3 days across 3 universities, and it had more than 200 students from 15 different universities, just the Algerian side. It was a marathon. There's 3 panel sessions and 7 workshops in total, where we interacted with students. We delivered the workshops. It was hands-on workshops. We had researchers there debugging codes, explaining codes, teaching, very focused on teaching them something, not just showing them something. Surprisingly, we also had a group of around 13 high schoolers that came to one of the panel sessions and attended the workshop. Those were not actually programmed. They came as an invite of one of the club in the last minute. The high schoolers were extremely excited and interested, and that kind of gave me joy. Seeing how interested and how passionate were they about learning. They were asking about quantum bell experiments and stuff. That gave me joy, and it shows that there is more to come in the future. I will talk later about the impact of this event and all of our outreach. We also had a member of CQTech and Q Algeria, Ashraf Bousahi, organized the first Algerian Quantum Hackathon in May last year. The event was held in the West it was organized by the club Google Developers Groups of Sidi Bel Abbas, a city in the west of Algeria. The format was 36 hours of non-stop innovation with one main quest that was how to apply quantum in Algeria and benefit from it. And there was 9 side quests that were like smaller problems to solve for people who did not have like extensive knowledge in quantum computing to think about the main quest. The side quests were there to teach them and give them hands-on. This was in May, 4th of May of last year. The impact of those events is what I'm here to talk about. Is like I'm here to show you that the effort we spend on education, we get the best return on investment to ever exist. It's not just about making startups. It's not about doing research. It's not about publishing papers or making SDKs. It's about helping the people and teaching them and giving them the opportunities that you wanted to have when you were a student and building for the future. And that's the true investments that we expect to get return on. Since CQTech started the last year, it started in 2022, what changed after since we started doing outreach? I mean, perhaps not exactly due to our efforts, but it correlates, and I'm just here to share that part. Then on the national impact, the country has launched 51 PhD positions in quantum computing last year for the first time, because that shows that there became an interest, a national interest in quantum computing, and the interpretation of quantum computing as a future technology has changed, and people are thinking that they should invest in it now, and that's a good sign for an African country. There was also a launch of I'm gonna finish. This is the last slide. Also, there was a launch of the first 2 years ago, the first quantum computing program in Algeria, a master's program in quantum computing that is mentored and supported by CQTech. We do deliver CQ trainings for them. We trained students there. We have even had 2 master theses work with Dr. Tahar Webah in our lab. We are seeing that like from people that we interacted with, there is a huge spike in interest. I'm seeing a lot of people, Algerians, competing in quantum hackathons, winning quantum hackathons, that more than I've seen before, and that is a really good sign. It shows that the continent is moving, the country is moving, the people are interested, and hopefully, and this is not just a presentation, this is a call to action to everyone here. Do your maximum on education and outreach. The people are interested. Just help them not lose that interest and help them not lose passion. At CQTech, we have successfully did the pipeline. We have like use cases of people who started as students throughout hackathons, throughout people, and I'm the best example of those. I started as a student who did not have any idea, and then some people from CQTech invested time in me. They taught me. Hackathons helped me. There was educational programs that they shared with me. They were patient with me, and now I'm doing research on quantum computing, and I'm presenting this to you, and I'm doing that. But that's it. What? Okay,
Right.
And thank you.
Right. Thank you for that, Muhayman. And just a reminder, please mute your mics if you are not presenting. Right. Some key takeaways. Did you say 5 or 3 first place finishes as international hackathons?
5.
That is tremendous. 5 solid first places.
Yeah.
Oh my goodness. I mean, CQTech just demonstrates it that they don't just produce one good researcher. It's produced a pipeline from the way I'm looking at it that keeps generating talent, wins, and credibility year after year. And Q Algeria is a model for national quantum ecosystems. A local keyword chapter rooted in university with community ownership, replicable, fundable, scalable, best return on investment, as you've rightly put it. Thank you very much for this presentation,
Thank you so
Muhayman,
much.
and wish you all the best.
Thank you.
Awesome. Yeah, so I believe sharing links to wherever you can locate them, learn about their work, get in touch, collaborate, or whatever leads that you want to jump on. Our next presentation is on Prep Desk Lab by Emmanuel Omolaja. Everything you might have seen today, every quantum algorithm, every hybrid pipeline, every hardware demo begins somewhere. And Muhayman was just talking. He said early on that some people took chances on him by giving him the resources, the education, and all of that. It always begins somewhere learning, possibly in a classroom. And right now, across Africa, classrooms are not equipped for the kind of hands-on technology-driven learning that produces quantum builders. Physical labs are too expensive, theory-only teaching is too limited. The gap between what students need and what schools can afford is enormous. And Prep Desk Lab is closing that gap, as you will see in a bit. Emmanuel founded Prep Desk Lab after experiencing Africa's tech education gap firsthand. As a student, his solution affordable, licensable, interactive digital labs, and he's going to go into the nitty-gritties. The platform is live at prepdeck.org, and he was also part of the HIGAS Fellowship and went to the Kwame Nkrumah simulation event as well. I believe the ecosystem is building a community. And yeah, over to you, Emmanuel. Let us hear from you.
Thank you very much, Atadana. Am I audible, please?
You're loud and clear. We can see your screen.
Right. Well, okay, you can see my screen too. It's a great privilege to be here. Very, very amazing project. My name is Emmanuel Omolaja, and I'm going to be talking about our project, which is PrepDex Lab. So PrepDex is a company dedicated to making personalized learning accessible for every student, every child, at prices that are honestly hard to believe, or for free. While PrepDex Lab, the product we are going to be showing today is sitting under PrepDex, is a free, ad-free online lab with simulators and training tools built specifically for African students. No paywalls, no ads, and no sign-ups. So we don't need to spend too much time on PowerPoint. Let's get to the lab. So, is my screen still visible?
Yes, it is.
All right, and it's showing on the lab, right? Just want to be sure.
Yeah, it's showing our lab with some desktop computers.
Okay. All right, so we are live. We have our web application online, which just go to prepdex.org, and you click on the lab. You would to navigate you to this. We currently just added a new additional lab yesterday, but we are still uploading it. Now let me take you to my best lab, which is the Newton's law. And as we first know, the first law of Newton, every object is at rest except acted upon by an external force. So we're going to reduce the friction. We're going to, let's reduce the force for a bit. The mass is all right, and let's run it. So when you are teaching a student on physics, the idea is to also have them visualize what you are teaching them, not only as theory, but also have the practical aspect explained to them. And this is one of our most basic lab, but for me, it's one of the most exciting one, because when I do this, when I reduce the mass and I reduce the friction, it keeps going. So yes. This is our physics lab. Let me go to our quantum computing lab. So we have our quantum computing lab, which I must say was made possible because of AQC. Thank you, Dr. Tokas. She helped a lot with this. Thank you, Farai. Thank you, Atadana, for your expertise. This is our foundational labs on quantum computing. So this is the block sphere. When you add let's put it on superposition, and you apply Adama gates, it shows you on the block sphere the direction it goes, and you can animate it. So the animation It's there, and you can also turn it around to see it. Like I said, the idea is for students, as you are teaching them, as you are going for your outreach, you also have something to show them. We have various labs here, and we have quiz too. We have reference things that they can read, timeline on quantum computing. We have our most fundamental lab, difference between a classical bit and a qubit when it's getting superposition and is measured, with explanations here and questions here. Now it takes a lot of resources and time to build this, but it's tailored to make sure that it's user friendly. Then we have our whiteboard in case you are in the middle of something, maybe physics, and you want to write. This is our whiteboard, which you can use with any mouse, with a stylus, with your hand, with a joystick. It motions, it moves, and it's very easy to use. Very soon we are going to be adding more labs. With the more support we get, with the more support we get, with the more funding and encouragement we get, we are going to be adding more labs. So we are going to have the quantum chemistry lab. We're going to be having the chemistry lab stand on its own. We're going to be having the mathematics lab. We're going to be having the algebra, different from the mathematics lab, and analysis lab. We're going to be having different other labs as we move. But how can you support us? One of the most important ways for you to support us is to use our lab and give us feedbacks. Use our lab on students, use our labs on your outreach, share it with your community, test our labs and give us feedback. What do you think we can do better? And we are also looking for fundraising. We are fundraising, also looking for grants and funding opportunities and partnership, not only money, but more of AI credits to help with the simulations and all of that. Now you can reach out to us through LinkedIn, PrepDex Africa, or email us at hello@prepdex.org or www.lab.prepdex.org. And that will be all. Thank you.
Thank you, Emmanuel. And Emmanuel is the architect behind the AQC digital experience. Every feature that works, every clean line you see on our site, that's his craft. And it is just good that we appreciate him publicly. He handles the heavy lifting on the code. If you find a bug or a feature you hate, that's on us. For the bad directions, blame not him. So that is it for PrepDex, and that is it for the program and presentations, right from health solutions to optimization solutions, to community development. Oh my goodness. From switching, is it essentially switching? People from different other backgrounds who are coming into quantum and developing amazing solutions. That is the ecosystem. I'm going to leave it here for Farai to nicely close it. So yes, Farai, if you are able to step in now, thank you. We cannot hear you if you're speaking.
Do you hear me now?
Right, loud and clear.
Okay. It seems like my headphones not behaving, but well, that being the case, no problem. Thank you so much for getting this over the line. Okay. All right. So we've been in this room for almost 2 hours and a bit above. In this time, what have we seen? Quantum classical pipeline screening for diabetic retinopathy in Africa, a quantum operating system for infrastructure optimization across 3 countries, quantum drug discovery for malaria built at AIMS, a qubit connectivity tool built by Ugandan engineer in Germany, a live BB884 quantum key distribution demonstration from Ghana's photonics labs, think that didn't come in, but we will have a link to these outputs that have not been presented today. The presenters had life happening as well, but I guess you know, the topological quantum simulator that we saw, fluxonium qubit research, which is cutting edge, really important work that is being developed by the top hardware companies in the world. And you know, we've looked at solutions for diseases, quantum random number generation, just the understanding of quantum to say where are we, what can we do, so that we build a solid foundation for education. We saw the work from the community, really prolific groups on this continent that are doing super well, collaborating around the world, leading and putting new ideas that other people are using out there. So this is the community, this is the ecosystem. Thank you so much for your support and for coming to join us. We now have a record. This is not the only work that's happening on the continent. There's much more. And we are still accepting this work to come so that we can add it to the repository. So please keep it coming. Please send us your work. Let's make this happen. What comes next? We've got a second quarter roundtable happening in June. I think links have been shared with you. We're going to be focusing very much on securing Africa's digital backbone, PQC and QKD, test beds, you know, just practical ideas on the migration pathways, you know, and what that looks like with the infrastructure and lack thereof in Africa. So we're convening stakeholders and looking for partners and ideas to make that happen. If you want to partner and, you know, get that to work, reach out to us at collaborate@africaquantum.com. Then we also have got you know, coordinators opportunities, champions opportunities, where people can come in and begin to build ecosystems through templates that come from, like you noticed, experts and people who have been doing this, like CQ Tech. They've got a template and they can help you replicate and optimize it for your own context and environment. We would encourage you, now that we're getting into the season of celebrating the World Quantum Day, April 14. Please host events, introduce quantum to somebody, reach out to us. We have all the resources, and this community is available at your disposal in your quest to introduce quantum and, you know, make it a reality for more people on the continent. We heard these stories of people that came into the room from, you know, interesting backgrounds and sometimes unexpected backgrounds and ended up falling in love with the subject. Why not give everyone an opportunity to fall in love with this subject, to get to be part of this community, to step up, to present, to share their work, to grow, to travel? Some people here started in hackathons, ended up traveling and going across the world. So we are here for you and would love to support you. The other opportunity is to be a quantum catalyst. So be a quantum catalyst during that build up to World Quantum Day. Let's make quantum a reality for more people. Let's expose people to this opportunity. Some other people don't even know that we are having these outputs and this conversation on the continent. It's our job to do this. I talked about the repository. Keep the work coming. The work doesn't end here. Send us your work. We want to put a repository which people can, you know, look at. They can cite, they can fund, they can partner, they can collaborate, they can give feedback, they can help you move the needle and move things forward. So keep sending your work. The link is being shared with you on where you can make this happen, so that we can have a public record available to everyone on the work that is being done by African researchers and those in the diaspora, so that our partners have this easy, you know, access and gateway into the continent for collaboration and for impact. So for the funders in the room, you know what to do. I think we had clear asks, and we're looking forward to, you know, seeing you taking steps to support, you know, the outputs that you see over here. Get them there to the point where they're fundable. Don't criticize the work. We are all doing our best to build. And I've not been in an ecosystem where people are perfect. Everybody starts from somewhere and there's work to be done. So your work is also cut out just like ours. Institutional partners, you know the ecosystem to back, you know the work we're trying to do. This is your moment. Step up, come forward, be ready to partner, and let's build and make quantum a reality in Africa and set up for global impact as well. Like we have realized, the solutions that are being explored on the continent have global impact. If you are hiring, the talent is here. If you are a mentor and you will provide access to hardware, here you go. This is the community. Bring it to us. We will reach out to this community. We will create that framework of making sure that there's a streamlined process of reaching out to all this talent and the other talent that is not even on this call and beyond. And to everyone, please share this, share the recording. We're going to send up, we'll send the follow-up information with the video on YouTube, share the repository, introduce people in this community, open doors, and stay in the room. Don't leave. Stay in the room and stay in the ecosystem. Keep supporting us. We really don't need anything else except the amplification and you to put hands on with us to build this community, to build Quantum, to develop our communities, to solve problems, and to make impact for humanity together. Thank you so much. It's been a pleasure and it's an honor to be able to work with you to deliver this impact and to showcase all the great work that's being done within the continent and outside, and all the partnerships and the collaborations, and just how we are learning about each other and learning from each other and supporting each other and growing together. Have a very good day. We've got a happy hour coming. I think links have been shared as well. You can come there, talk to the speakers, get to ask questions, and just experience this community beyond this event. With that, I appreciate you all, and a great weekend and a great day. Thank you.
Right.
Goodbye.
Thank you very much. Right.
All right.
Goodbye. On behalf of Africa Quantum Consortium, our regional leads, our fellows, our quantum circle coordinators, Quantum100 Honorees, every member of this network who has shown up, stayed committed. Thank you for being in this room today, and see you at the happy hour in a bit. Enjoy the weekend.
Goodbye. Thank you so much, everyone, for attending, and thank you for the organizing for putting this together. Thank you, Farai, and thank you, Tadana, and everyone who's behind the curtains. And goodbye.
Thank you so much, everyone. Have a good day. Blessed.
Thank you all. You have a good one.